be here. So let's jump right in. One thing that we've seen a lot of our customers face is just this question of what it means to do production grade LLM serving or inference. And here at Predibase, we like to break it down into sort of these few core components. So to get started, we think that there needs to be sort of high reliability, security and privacy, hardware flexibility, fast cold start times, and observability and metrics. But most importantly, there really needs to be blazing fast performance. And what we want to walk you through today is how we achieve this at Predibase and how this is all cornered on our Inference 2.0 engine, which we are very excited to share with you guys, and sort of sort of show how this has really unlocked a new level of performance for us. So to jump right in, one of the critical components of having a production grade inference stack is having the right hardware for the job and then auto scaling it correctly so that you are not overpaying. And Predibase works with a variety of cloud providers to secure a variety of GPU types. So what this means is that we have gone out and worked with different vendors and different cloud providers to ensure that there are the right GPUs available for the job. So if you're serving a small model, you can use an A10G that comes at a fraction of a cost to something like an A100 or an H100. And so you're able to utilize the right hardware for your use case. And then the thing that we have built, which is very useful, is intelligent auto scaling. So based on the load that your replica is experiencing, we auto scale the GPUs up and down based on some pre-configured settings that we work with our customers on, but B, on the actual traffic that is going through the LLM to ensure that you are not wasting time on idle resources, and but also are always properly provisioned to be able to best serve your customers effectively. Now, another big problems we've seen our customers face is like auto scaling is great, but if it takes the model 10 minutes to scale up, then what's the point? You know, you might have a 20-minute peak time of the day where you need sort of 10 GPU replicas running at the same time. But if that's not the case, that's not useful. And so we've broken down what goes into contributing to these slow cold start times and have done a very good job at sort of cutting those down. So we broadly think of it as that there being 4 parts: sort of acquiring the node or getting the right GPU ready, then downloading the container depending on sort of where the GPU is located and how it's been configured. This might take a bit of time, downloading the model weights, and then starting the model. And what we've done is that we have an existing pool of nodes that we keep warm to mean that when you need, that means that when you need a new node, there's it doesn't take 2 to 3 minutes. It's down to 5 seconds because this is already in our pool of available GPUs. We cache our containers very aggressively on disk so that no one pays the download time of the containers, especially with these big containers that are running things like Torch and a lot of these optimized inference frameworks. They can be multiple tens of gigabytes in size, and so this really cuts down on the download speed. And then lastly, sort of we aggressively cache the weights as well, which means that you only pay the cost of starting the model, and that can happen in seconds. It's very, very fast. And so it means that auto scaling is very effective. You're not wasting idle time, and it can really respond to the load and sort of any spiky traffic. Lastly, furthermore, it's very important that there is clear observability into your deployment. And this sort of goes back to the question of saying, like, how do I know that my LLM is working? And you want to know sort of the events of the LLM, you want to know the performance of the LLM, and lastly, if something happens, you want to be able to very quickly assess what is going on. And so we've addressed this by providing these in-app histories that allow you to see exactly what is going on with the node and with the deployment. We have also we also provide these in-app metric graphs so that you can very quickly tell if the performance of the LLM is up to what you've expected, but also audit and see how users and your product is using the deployment, and if it's able to service your use case in the way that you need it to. And then lastly, if there's anything going on, you have direct access to the logs of the deployment, so you can go in and see, what is going on, which adapters are being called, and depends on sort of the configurations that you've worked with us on, what you can see there to be able to peel back this layer of abstraction and see exactly what's happening on the machine that's running your LLM. Another key important part that we've spoken about is stability and reliability. And the way we've thought about this is over the years, we've seen so many different failure modes that people run into with deploying these LLMs. And we've hardened our deployments to be able to be extremely resilient to all of these different failure modes. So we focus on doing rolling updates so that if there is any problem with an update to the deployment, there are existing deployments, there are existing replicas that are unaffected and you can still service your customers. We do continuous health checks so that if a deployment gets stuck, it gets very quickly restarted so that this does not affect your production workloads. And we are able to boast a very high SLA to reflect this. We do network level retries as well, so that if there's a problem on the network level, we are able to catch that quickly. We have high availability backups, so we deploy replica clusters in different regions in case sort of with one of our vendors or something that happens where there is a cluster-wide problem or a region-wide problem where our data plane can go down at the data center. It ensures that your service is unaffected. And then one thing that we've all seen is that sometimes if you're sort of pulling models semi-regularly from Hugging Face, there have been a lot of disruptions in the past. And so what we've done is we've cached and replicated the model weights to ensure that even if there's an upstream disruption on a third-party vendor, we are able to continue to service our customers and their sort of these mission-critical LLM inference use cases. And then lastly, around security and privacy, one thing that we have championed is being able to do all of this inside your VPC. So the Predibase VPC is our offering to be able to run the Predibase cloud inside your own private cloud, or the Predibase offering inside your own private cloud. And what that allows you to do is you get the latest open source models, you get the latest proprietary fine-tuning stack, and you get all the software optimizations that we have put in on hardware that you fully control and on network configs that you fully control with complete sort of visibility into what's going on. So we work with you to deploy that directly into your AWS, Google, or Azure account and run it in there. This provides sort of full data isolation, so none of the data ever leaves your cloud, and it means that your security team can sort of rest at ease knowing that if this is a very if this use case is sort of very security critical, or there are a lot of regulations around that, you can sort of in-house the whole thing and feel very comfortable doing that. And we're doing this with a few very successful customers that have really enjoyed this. But again, all of this means nothing without a very fast underlying inference engine. So we have sort of put out LoRax before, and people have seen a lot of success with that. But we've taken it a step beyond and really gone after performance in a very aggressive way. And with our Inference 2.0 stack, what we have done is we've started with a fork of vLLM, which is an open source LLM inference project that really the community has gathered around. And using that, we have done a lot of work and added key optimizations to unlock sort of best-in-class open source model inference. So a few things that we have done is we've added TurboLoRA support by rewriting the entire speculative decoding flow in vLLM. We'll give you a refresher of what TurboLoRA is in a minute, but it's just sort of speculative decoding plus LoRa's to unlock sort of best-in-class inference for your own fine-tuning. We've added support for chunk prefill with speculative decoding, which is chunk prefill is this awesome optimization that allows you to keep your GPUs fully utilized and really increase speed, but it's notoriously incompatible with speculative decoding, and we've spent a lot of time figuring that out and gotten that to work. And we also allow for this sort of what we call multi-turbo inference, which means that you can serve multiple speculative decoders simultaneously for different tasks, so that similar to LoRax, on your base, if you have one base model, you can have multiple speculators and multiple LoRa's to do multi inference, so that you can get multiple fine-tuned models on one underlying base deployment. And what this allows us to do, and the upgraded features for our customers, is that with our Inference 2.0 engine, we have much better support for embedding and classification models, which we're seeing more and more become this very important part of a larger AI strategy when people come to their inference providers. We've seen across the board faster inference times over LoRax, our original open source inference library. We've seen state-of-the-art inference speeds for LoRa serving. So if you're interested in serving a LoRa really fast, we're able to serve you much, much better than before. We've upgraded speculative decoding to unlock even faster inference. So our optimizations within Inference 2.0 have really unlocked faster speeds. And then again, going back to that chunk prefill prospective decoding combination, this has really been the foundation for a lot of these speed ups that we've seen. And with all of that, I'm excited to turn it over to my colleague Chloe, who will be sharing screen now and walking you through the rest of the presentation. Thank you so much.
Yeah, thank you, Magdi, for the great overview and highlights for our Inference Engine 2.0. So now that we have seen what Inference Engine 2.0 can do, let's take a closer look at how it actually performs, right? And what kind of secret sauces went into getting us there in terms of speed. So before we dive into the real methodology behind the secret sauce, let's do a brief recap on some of the key concepts about adapters. So most of you are already familiar with LoRa fine-tuning technique, which is the key technique our Predibase platform focuses on in terms of fine-tuning. It's a very powerful technique to specialize model outputs for quality improvement on specific tasks. Very good when you want to fine-tune without touching the full model weights for efficiency purpose and being able to maintain the same high quality of the model output. But what if quality isn't your only concern? That's where Turbo comes in here. So Turbo introduces parameter efficient speculation, which is our way of speeding up inference without having without having to retrain or swap out your model. So instead, you just need to add additional layers on top of your base LoRa as a lightweight way to boost throughput, especially very important when you are serving high traffic workloads in production. But of course, in real world, you want the best of both worlds, right? So that brings us to TurboLoRa, the third concept, which is a hybrid approach that gives you both high speed and high quality. And with TurboLoRa, you can jointly train your LoRa weights as well as your speculators, therefore optimizing your model to deliver both high quality outputs and at a very significantly lower latency. And TurboLoRA is actually the main secret sauce of Predibase platform. And this flexibility means that you are no longer facing the trade-off between performance and precision. You can actually get both, and you can adapt and choose which one you prefer based on your specific use case. And now let's talk about Medusa. So if some of you have attended some of our previous webinars, you might have already seen this slide, this diagram, and heard about TurboLoRA, and also the implementation technique behind it called Medusa. And just to provide a brief recap on what it is, right? So for training the Turbo Speculator, instead of training separate models, we train additional layers added to the original LLM called Medusa heads. And those are parallel lightweight decoding modules to generate multiple prediction tokens in a single forward pass instead of the normal next token prediction that a normal LoRa does. So here in this diagram, you can see we have Medusa 0, Medusa 1, and Medusa 2. And each of these Medusa heads is responsible for predicting the next few tokens, over, the, and lazy, all in parallel. And meanwhile, the LM head is still predicting the immediate next token, jumps. So this parallelism enables faster decoding without having to sacrifice the model quality, and the approach is fully compatible with the existing transformer architecture. And in terms of training the Medusa head, instead of training a generic Medusa based on the original LLM's training data, which is the original approach we employ when we first developed the Turbo, we gradually improved the method, and we also employ a self-distillation approach to train our customized Medusa over time. And how it works is that we start by creating the self-distilled dataset by sending the prompts from some of the most common public datasets from Wikipedia, for example, to generate responses, right? And this will become our self-distilled dataset from the LLM we want to train on. And then we take the self-distilled dataset and feed it back to the same LLM to train the Medusa heads. They generate logics based on the base model's representation. And the outputs are compared against the actual labels. And during the training, we also calculate the loss. So this training process and this overall approach, self-distilled dataset, training the Medusa for a more customized Medusa heads. So this overall approach allows us to reuse the knowledge of the frozen model when only training the lightweight Medusa heads for improved inference time performance. So we don't have to train separate models. And then with all this context and recap, I would like to start presenting some of the real benchmarks we did on comparing the general Medusa versus, the customized Medusa. And also I will present some benchmarks on comparing the LoRa, the Inference Engine 2.0 versus some of the competitors in the market. So let's begin by looking at the performance gains introduced by, generic Medusa heads. So on this chart, we are comparing the base model's throughput measured in tokens per second against the same models augmented with the generic Medusa. And in these two bar graphs, you can see consistent improvements across both use cases, right? So on the left, we have the Con LLPP use case, which is a name entity recognition use case. And throughput increased from 70 to 93 tokens per second. And for Magic Coder, which is a text to code use case, throughput also rose from 71 to 117 tokens per second. So these are the general improvement results we saw from early benchmarks by benchmarking the general Medusa. And this results suggest that even without task-specific optimization for Medusa, the generic Medusas offers a substantial boost in generation efficiency already by just reducing the decoding bottlenecks. And building on top of that, we now can introduce the task-specific Medusa to see how it further improves speed compared to the generic Medusa. So as I mentioned in the previous slide, the task-specific Medusa fine-tunes to each task by training on the self-distilled dataset. And on the same two benchmarks we saw previously, you can see that for ConLLPP, the throughput jumps significantly to 147 tokens per second for the task-specific Medusa, which is an approximately 60% improvement over the generic version. And then for Magic Coder, we also see a huge gain, right? So reaching 130 tokens per second, up from 117. And this also demonstrates that when Medusa is tailored to the underlying task structure, we unlock even greater benefit in terms of accelerating the speed during inference. And after looking at, comparing the generic Medusa versus the specialized Medusa, we also want to look at how this optimizations of the new inference engine translate to the real world latency across different providers. And here I want to present some benchmarks regarding, comparing our new inference engine versus some of the other inference providers in the market. So here we actually benchmark a real world customer use case on our Inference Engine 2.0, on Fireworks, and also vLLM. So the use case is preference matching explanation. You can imagine examples like the input of the model being, for example, a job match to a candidate, and the output of the model should explain why the job is a good fit for this candidate profile, or why the candidate is a good fit for the job. Or in another example, you can imagine, for example, in matchmaking services, the input being, okay, two profiles being matched, and you expect the model to generate an explanation of why the two profiles are good matches, right? So things like this. This is called preference matching explanation. And then we also benchmark on a token distribution profile of around 350 tokens input and 50 tokens output. And we benchmark on one single H100. And for all the latency benchmarks we show in the next slide, all the numbers are server processing time without considering any network latency. And most importantly, as Magdi mentioned previously, one of the most important feature we enable in the new inference engine is called trunk preview, which lets the model to start working on your requests much, much faster by breaking your input into smaller chunks and feeding them into the model piece by piece instead of all at once, which keeps your GPU fully utilized during inference time. So with all these assumptions, we can actually look at the real benchmarks that we got from this exercise. So this diagram shows the P95 latency across a variety range of QPS requests per second. So ranging from a single request to 5 to 10 to 15 and all the way to 20, because we also want to test how the deployment performs when it scales up to the real production traffic workload, when the traffic gets overloaded, right? So that's why we benchmark at different QPS levels. And we compare 3 different inference providers. So the Predibase-based model, the Predibase TurboLoRA model variant, Fireworks-based model, and also vLLM-based model. And as you can see in this chart, across all QPS levels, for Predibase, the blue bars and the red bars, we consistently delivers the lowest latency numbers, and we remain pretty competitive even at higher QPS levels, which means our inference engine scales pretty well when the workload becomes heavier. And for Fireworks, which is the yellow bar, Fireworks base model actually remains pretty competitive at lower QPS, but it shows much higher latency under higher load, which suggests that it is less efficient scaling up. And for Fireworks, I also want to mention for the Fireworks benchmarks were generated on a self-serve deployment that I spun up on the Fireworks platform using all the defaults. So I did not do any manual tracking to try to optimize the deployment. So when you look at these numbers, this is one of the consideration you need to take into. And then lastly, for vLLM, so as many of you already know, vLLM is one of the most popular open source inference engine in the market. And we also spun up a deployment on RunPod's serverless GPU platform for vLLM. So this is actually vLLM deployment served on RunPod. And as you can see, so the green bars numbers represent vLLM latency. And for vLLM, you can see even with vLLM and RunPod's GPU support and availability, it turned out to be underperforming across the board when I use the self-serve deployment. So this comes to like one of the most common questions we get asked by customers, right? So a lot of customers compare us to, open source inference platform like vLLM and ask like, okay, vLLM is open source and GPU resources are widely available. So what are the key advantages of using a fully managed inference platform like Predibase, right? So during this exercise, I hope, and also based on these numbers, I hope the key takeaway is that the user experience in general, by self-serving the deployment through vLLM on RunPod, and also all the benchmarks tell us that building a reliable and scalable inference setup for optimizing the performance can still be very, very challenging. So you have to, since it's open source, it's not fully managed, it's user managed. So you have to deal with a lot of challenges like model compatibility, performance tuning. You have to do optimizations yourself, and you have to figure out a variety of operations burdens, things like infrastructure, configuration, observability, all the features that Magdi just talked about. We take care of all of this for you. Whereas if you use open source inference platform like vLLM, you have to take care of this all by yourself. And also you have to deal with, all the API integration complexities across different platforms, because for this exercise, I use RunPod as our GPU renter. And this overall, this results reinforce that Predibase's end-to-end optimization stack, especially when it combines with TurboLoRA, enables both high throughput and low latency, making it a very, very strong choice and platform for any production ready inference workloads and use cases. And then just to conclude the whole presentation, the future of LLM inference. So what are the key takeaways after you hear about, the LLM inference bottlenecks, our latest inference stack, and also after seeing all the numbers and benchmarks by comparing, different providers. So here are some key takeaways from us, right? So the first thing is the base model inference is increasingly commoditized. The future of LLM inference is moving towards greater efficiency and accessibility. Based on tools like, vLLM and TGI, and GPU is very, very accessible right now. Infrastructure is no longer a differentiator for inference. And the second thing is the real gains come from optimizing for your own stack through co-located training and serving, which improves performance and simplifies deployment. And finally, I think the biggest speed and quality improvements come from training on your own data using advanced techniques, like TurboLoRA, speculative decoding, which allows you to unlock up to 4x throughput gains, which can be fully achieved on the Predibase Inference Engine 2.0. So with that, I would like to conclude the presentation and open it up for Q&A.
Awesome. Thank you so much, Chloe and Magdi. Folks, as a reminder, we see some good questions coming in the Q&A tab. Please feel free to drop any in there, and we will try to get through all of them as they come up. So let's see. One good one is, asking kind of how Predibase is different from companies like CoreWeave and RunPod. And I think I'll take a first stab at that one. Magdi or Chloe, feel free to layer anything on top of it afterwards. But those two in particular, and others kind of similar to them, really specialize on making GPUs as easily accessible as possible, so that you can go out and rent an H100, an individual GPU rather than a full node of 8, for example. It just makes it easier for you to get a GPU. But then from there, for the most part, the orchestration of training and serving and optimizing your models is your responsibility. So they make the GPU infrastructure fairly easy, but it is a little more bare bones than, for example, Predibase, which is really built from the ground up to unify fine-tuning and serving in kind of that continuous loop. So, RunPod might help you quickly get a base model into production very quickly. But with Predibase, you're going to get access to those best-in-class optimizations for fine-tuning and all those optimizations for serving also. Plus, we have that VPC deployment option, which there's another question related to. But Magdi or Chloe, anything you'd want to say on top of that?
Yeah, I would say that pretty much summarizes it. I think the key summary is that for Predibase is a fully managed fine-tuning and serving open source LLM platform. So we specialize in developing LLM applications, whereas RunPod, as Bill mentioned, is a general purpose AI workloads platform. It doesn't provide some in-depth features for training, for example. So as a user of RunPod, I mainly use RunPod when I need GPU. So it's pretty much like my GPU renter for me. But for Predibase, we really specialize in fine-tuning and trying to make it the best. And also we also specialize in inference LoRa-based serving and try to do a bunch of optimizations on top of any open source libraries.
Awesome. Thanks, Chloe. Another one, Magdi, this is probably a good one for you. Question from EJ. With VPC, does your Inference 2.0 engine also deploy into the VPC?
Yes, we are able to deploy it both in VPC and in the Predibase cloud. And with the VPC offering, we make sure that there is availability of the different GPU SKUs that are needed in your hosted cloud, in your chosen cloud environment. But other than that, everything is fully compatible.
Thank you. Another good question from Samuel. Does Predibase support vision language models? Short answer to that is yes. Magdi, is there anything you want to add, or Chloe, add on top of that?
Yeah, we do support vision language models. We so far support a few different models like LLaMA 3 to 11 billion. And we are working with a few customers on some of the vLLM use cases. So if you have a use case that is a good candidate for vLLM, please come talk to us.
Awesome, thank you. Let's see. A lot just came in real quick. vLLM made a large update recently, the V1 engine. Did we fork before or after that update?
We are supporting the V1 engine. We are working on making on rolling that out. But we do support the V1 engine forked after.
Awesome. Let's see. Okay, here's one that could be this one's a mouthful. I understand LoRa is for fine-tuning large models efficiently without retraining all weights. How does speculative decoding work, and how does TurboLoRa's joint training differ from using LoRa and speculative decoding separately? Are Medusa heads dynamically allocated based on sequence length or token entropy? And what loss functions are used during Medusa head training? There are about 3 questions in there at once, but Magdi and Chloe, it's in the Q&A tab if it's helpful to reference.
Yeah, I'm happy to take that on. I think what makes TurboLoRa so effective is that each LoRa comes with its own separate Medusa head. So, and when they're trained together, what happens is that you are able to constrain the output of the Medusa head to the domain of the LoRa. So let's say you're training a LoRa to properly predict, to summarize sort of movie reviews or something, and you're using like a LLaMA 3 model. Using a base speculator is very good at getting LLaMA 3 to be faster at its general domain. But then if you're focusing on a much smaller domain, the Medusa heads work a lot better because they are able to predict much more accurately the in-domain answers. And then because they're paired with the LoRa, it means that you are able to effectively speed up the performance in the domain of the LoRa, but then if used outside, it wouldn't do as well. So it's just this hyper optimized way of serving the model. And then what we do is we are able to serve multiple of these LoRa's and TurboLoRa's simultaneously. So if you make a request to LoRa A and LoRa B, each one has its own Medusa head. And so each one uses the correct Medusa head for its own inference. So you get the speedups across the board. Using it separately would be different because if you had one general Medusa head and you're using these LoRa's against that one Medusa head, it means that the accuracy of getting in domain words correctly goes down, and so your hit rate goes down, and so the speculative nature of it doesn't become as effective in speeding up inference.
Awesome. Thanks, Magdi. Love that. Magdi, here's a related one. What are the effects of loading heads and Medusa heads in terms of latency or adapter size?
The effects it's mostly on memory. It's not on latency because these are very small layers. And so if you have the memory budget for them, you can store like a lot of them, and we do some very smart cache management to make sure that when these LoRa adapters are loaded in or loaded out in the Medusa adapters or whatever, you have the right ones for the job at the time of inference. So latency wise, it's you don't really pay much. What you do pay for is a small increase in memory footprint, but that's something that sort of you figure out at startup time, or we figure out at startup time, so it doesn't impact the model performance.
Thank you. Let's see. Just pulling through a couple others that are a little specific to use cases and following up with you guys directly. Let's see. One is, does Predibase share any code samples, papers, articles, etc., where it's possible for developers interested in learning more about these optimizations by looking at code? I'd say some of this is covered in, we have some content around this on our blog where we talk about, some of the advancements we've put into the platform, and we have a bunch of different tutorials, and also we have in our documentation, we have a bunch of different tutorials that let you kind of play with some of these optimizations and help you get started. And then some of these optimizations also are just kind of baked into the platform, in a way that's not open source. So answer is, check out our docs, check out our blog, and then also feel free to reach out to us directly if there are parts of the platform that you want to learn more about.
And I would also say on that one, like if you're interested in looking at a lot of these optimizations implemented, looking both at the LoRax repository and the vLLM repository will be very, very helpful.
Absolutely. Right, folks. If you have any other questions, feel free to please put those in the chat or the Q&A tab. Just looking through to see if there are others that we can answer on the phone here. Let's see, Magdi, can you take a look at that one that just came in on the Q&A?
Yeah. So on the question around instruction tuning, we support instruction tuning, and we actually have done a big push on what we call RFT. So I would highly encourage you to take a look there and get in touch. We would love to sort of show you all the really cool stuff that we've done, mixing exactly that, doing TurboLoRA inference on LoRa's trained with instruction tuning. Look, my expectation on accuracy, it's very hard to tell without knowing the specifics of the use case. That with instruction tuning, you do sort of operate in like a more data scarce environment, but there are ways to sort of figure that out and properly set up like a reward model and do a lot of that stuff. Sorry, I was talking about you can do all of this using sort of RFT or more reinforcement fine-tuning based approaches. And then come talk to us. We'll show you what we can do.
Awesome. So do you have use cases mainly for text to text? Do we have a demo for text to voice?
Yeah, so voice model is actually the next modality we are looking into right now. So I think it's coming soon. Stay tuned.
All right, folks, still have time for more questions if there are any. As a reminder, this session is going to be posted on our YouTube sometime later today. We'll make these slides available also. And we appreciate everyone for, taking time out of their day to join us and learn a little bit about what, next gen inference looks like. And let's see, one more question just came in. Is this integratable to adaptive tuning? Magdi, can you answer that, or do we need more clarification? Magdi, you're on mute.
Yeah. I'm not quite sure what you mean by adaptive tuning, but I'm happy to, if you can maybe explain a bit more, I will happily give you some more context there. Yeah, in terms of question around the Git repo for the demo, we will be rolling out user guides on all of this in the next 24 hours that we can share more broadly. We will be emailing out sort of the attendee list with those resources that we are very excited to share. The Inference 2.0 engine, it is an updated version of our inference stack, so it is deployed either in VPC or SaaS. So it's basically like it's an optimized container for LLM inference, and so wherever the GPU lives, it sort of is hosted on the GPU. So it works both on VPC and SaaS.
Thanks, Magdi. All right, well, folks, thank you very much again. Looking forward to seeing you back at our next webinar, which we'll be announcing soon. Thanks so much for all the questions, and really looking forward to keeping the conversation going. If you have any other questions, feel free to contact us. You can go to our website. We have a chat in the bottom right there that goes to our support team. Feel free to request a demo if you have a use case that you think could be an interesting fit for what we've talked about today. Or find any of us on LinkedIn, and happy to keep the conversation going there too. All right. Thanks so much. Everyone take care.